So, okay, so we were asked to talk about the topic of what is dark matter, like how do we know it's there and what do we know about it, which is one thing that we both work on individually, but also have done quite a bit of work together on. But I wanted to start out just as this is a pretty broad audience with like just, you know, a basic picture of our universe from the Big Bang to today and what we think it's made of, and then go into like what the dark matter question specifically. So our universe is, we think, something like 13.8 billion years old, starting from the Big Bang. And originally, shortly after the Big Bang, the universe was incredibly small and incredibly hot. And the Big Bang started out, our universe is expanding, and that expansion started with the Big Bang and has continued ever since, but with different components kind of dominating that expansion over time. But you know, that very early universe is basically just energy, just radiation, extremely hot. But as the universe expands, it cools, and there have been a number of like
I'm listening.
Phase transitions that have occurred through that process. So after, you know, just the first microsecond-ish, the universe is cooled enough that you can actually start forming particles out of that energy. And then a little later, fraction of a second-ish, the universe is cooled enough that those particles can start getting together and forming like the nuclei that eventually will make atoms. So you make the very first light elements, only basically hydrogen and helium and trace amounts of lithium, but then everything else on our periodic table is made later through stars, through stellar burning. And then there's a very important transition about 380,000 years after the Big Bang, which is when the universe has cooled enough that electrons can bind into atoms. So at that point, our universe becomes electrically neutral. And there's still some of that original radiation, that energy left over at that point, which is now free because without the ionized universe, we don't have the photons scattering off of those charged particles. And that radiation is still around today. It's called the cosmic microwave background. So it's now the universe is cooled such that that's at a temperature of 2.7 Kelvin, so just a little bit above absolute zero. But that really gives us an imprint of what the universe looked like very early on after the Big Bang, and benchmarks a lot of our cosmological models, because then we have to take that and evolve it forward to what we see and make that work. So then, you know, all of the beautiful stars and galaxies that we see, particularly in visible light, when we look out on the night sky, didn't start forming until a few 100 million years after the Big Bang. And then I'll talk a little more about structure formation because it's one of the things I work on, and because it's very important to understanding things like what is dark matter. But because of the gravitational effects that those stars and galaxies start clumping together to make more and more complex structures as the universe evolves. And then
like
here we are today. Yeah.
A basic question.
Yes.
So there's all this heat.
Uh-huh.
It cooled. So what happened to the energy that was the heat?
No, it's still there. It's just at a lower temperature, but in a bigger volume. And a lot of that energy actually goes into making the particles. Like all of the particles we see came out of that energy. Although it is true that energy conservation on the scale of the universe and the universal expansion is a little complicated.
Okay.
Do you want to add anything to that?
Broadly, you know, it's sort of like in an explosion, you know, you conserve energy, but you know, things cool down right after the explosion, but the energy is still there. It's just, you know, diluted away by the fact that you've got a much bigger container.
Right. So dilution would be kind of the best way to.
It's the-
Okay, that
Yeah.
makes
But there
sense.
is conservation of mass energy from the Big Bang onward.
Yes.
More.
He's hesitating.
Well, I mean, dark
More-
matter would be part of that, I guess.
Yeah, I mean,
Conservation.
well, you also have like black holes and things that it's more or less yes, but like I mean it's
Yes.
Yes.
There is energy
Yeah.
and mass conservation. The one subtlety is, what we call the universe being defined as stuff that was at some point in causal contact with us. In other words, if you have something that is farther away, that the age of the universe times the speed of light, that is, outside what we define as the universe. But within what we call the universe, which is, anything within, where the speed of light, that ensemble of stuff conserves mass and energy.
If you add it up in the right way, because like black holes don't, like things
Yeah,
that
you
sink
gotta
into
have
black
like-
holes don't really talk to us anymore, and it gets a little,
I think you just said, we know there's stuff that's beyond the edge of the speed of light times the age of the universe. Is that
Mhm.
correct?
Yes,
And-
Well-
and
We
how
don't
do
know
that?
that, there may be.
there may be,
Okay,
but it is uninteresting to us.
no, but
because-
there's already the observable. I mean, there's what started out in, that was in causal contact in the Big Bang, but the expansion means that things that are farther away appear to be receding from you faster and faster. I'm going to get to that in a second. So it's also true that there's the observable universe where if you get to the point where something is apparently moving away from you faster than the speed of light, you can't ever observe light from that. And that's not necessarily the entire universe that was connected to us at the Big Bang at this point. All right, slide one. Okay. But this is great. So the basic composition of the universe is often represented as like a little pie chart like this. So the stuff we understand, all of the particles in our standard model of particle physics, all of the things we're made of, is only about 5% of the energy density. So we'll talk about this in terms of that energy conservation, energy density of the universe. And only a very small fraction of that is in like heavy elements. To astronomers, anything heavier than helium is metals, that's heavy elements. So that's a very small fraction of that energy composition of our universe. Most of the matter, most of the mass in the universe is in dark matter, the topic of our talk today, making up still only about a quarter of the energy density of the universe. The rest is in something we call dark energy. And we won't talk about this today. That is actually another topic that I observationally work on constraining. And honestly, in terms of understanding dark energy, compared to like everything we can tell you about what dark matter is and isn't, we're kind of in the primordial days of trying to study dark energy, just understanding like on the universe's, like on the universe scale, like its effect on the expansion and what that tells us about how much there is, and basic questions, how much that there is and has that changed over time is where we are in dark energy, not farther than that. Okay, so this is, our kind of standard model of cosmology today in terms of what the universe is made of. And if you talk to Joel will dub this the double dark model with dark energy and dark matter making up most of the universe. Okay, so just to talk about, so we talked about the observable universe, and that has to do with the expansion. And so when you talk about, like, you try to have, kids or general public visualize that expansion of the universe, often people will talk about it as like the blowing up of a balloon. But then you're like, you have to think of yourself on the surface of that balloon. So I like the raisin bread analogy. And so think you're baking raisin bread and you have your dough, and the raisins in that dough are the galaxies. Okay. And so what happens is, what we see is that galaxies farther away from us appear to be moving. They're receding from us at some speed, but it's not really that the galaxies themselves are moving. It's that the space in between them is increasing. So this is a very simple cartoon of, I have my raisin bread dough. There's some separation between my raisins, and then I stick it in the oven, and in some time frame, it doubles in size, right? And so, if you had a raisin that originally, so you have a raisin that was originally unit 1 away from you. And so there's like your local raisin. And then if the amount of space in some amount of time doubles, then, you know, a raisin unit 1 looks like it's moving at some speed, but a raisin that's, you know, 2 units away from you looks like that amount of space is double. So the speed at which it looks like it's moving away from you is double. So that's how we observe the expansion of the universe. And in fact, tracing that expansion over time is how we understand a lot about, you know, what the universe is made of. Because mass, for example, the dark matter, gravity would slow that expansion down, whereas dark energy is something that pushes out. And in fact, the expansion of the universe now, so for much of the history of the universe, dark matter was slowing things down, but now because the mass gets more dilute as the universe gets bigger, the effect of dark energy is now dominating, and the expansion is actually going faster and faster.
So Barry, this kind of puts your question into an interesting perspective. If you think about the raisin bread as being your mass to energy quantum of the universe, you know, it expands. You're not creating any new raisin bread. It's just that if you take the same amount, the same volume initially and later, you get a lower density. But you know, there's no mysterious energy that flows in or out of the system.
So
Yeah.
I heard you say that the galaxies aren't actually moving apart from one another, but isn't the redshift how we measure the speed that they're moving?
Yes, well, because the redshift, yes, but the redshift is the cosmological redshift has to do with the fact that that space is expanding, and so it changes the wavelength of light from, you know, it was emitted from, you know, some other galaxy, you know, I don't know, hundreds of years ago, even more, millions of years ago. And then it had to travel to you through a space that was expanding. And so that changes the wavelength of light by the time it gets to you. So it's it's actually really, you are, with that redshifting, you are observing that cosmological expansion.
Okay.
Yeah. Yep. Anything else?
Slide number 3.
Another thing. Yeah. Okay. So yeah, structure formation. So as that universe is expanding, all of the beautiful wealth of structure, like galaxies and what I work on are even larger clusters of galaxies, are forming through gravitational collapse. So at the epoch of the cosmic microwave background and earlier, the universe is almost exactly the same everywhere, not quite, but it really looks much like, this is a universe simulated in a box, computer simulation. It really looks like, I mean, you can't pick it out by eye, but there are like some slightly denser and slightly less dense regions in this box. But generally it's almost, you know, it's basically like a pretty uniform cosmic soup. But as you run time forward, the dense regions pull together, the stuff gets pulled out of the underdense regions. And what you see is what we call the cosmic web. So this beautiful, rich web of structure where like little dots in here are probably the scale of galaxies. And then you have, you know, bigger structures and filaments. And I just want to point out that, you know, Joel, who's on, I know, and some of our other faculty at UC Santa Cruz have actually been really instrumental in a lot of these cosmological simulations. In fact, Joel and collaborators have, I think, what's probably still the most accurate cosmological simulation, where you're looking at the evolution of the universe in a box. And that's really what we need. That's the theory that we compare to when we're trying to use structure formation to understand cosmology. So this is a strength of UC Santa Cruz. Okay, so what you get in the end is this immense cosmic web of structures on all scales. So the very largest things that form, this is a zoom in at the nodes of those filaments, and the very most overdense regions are called clusters of galaxies, literally because we see them in visual light as a bunch of galaxies all orbiting in the same place, right? And those, the massive clusters of galaxies, just to benchmark, can have masses 10 to the 15 times the mass of our sun. So, you know, thousands of galaxies, and then most of the mass in dark matter. And on the other side, you get what are called voids, these relatively empty regions. And so as I'll talk about mostly dark matter today, but this history of structure and formation really is very sensitively tied to that evolution of the universe and what the universe is made of. And not exclusively, but a lot of my personal research has used these clusters, these biggest structures, both for things like understanding how much dark energy there is and also knowing more about dark matter. Okay, so now I'll turn to dark matter. This is just a pretty picture just to get us started of a gravitational lensing effect. So this blue ring is a background galaxy. So this is one galaxy. In the background, you can see the light from this massive galaxy here, but there's also much more mass, obviously, in dark matter. And so that the light from that background galaxy gets bent, the path of the light gets bent as it, by that foreground mass acts as a lens, and you get a beautiful Einstein ring. So this is a picture of the galaxy lensed by the dark matter. So it's a really clear picture that there is, significant mass there.
So incidentally, it's the same galaxy duplicated 3 times, right? So there's this blue galaxy somewhere in the back, and its light gets multiply lensed by the intervening mass.
But this is actually really that galaxy stretched out. I mean, some of these knots are probably the same knots, but you can see, actually, I would say there's an arc here and then another arc here.
Is that a simulation or a photograph?
That's a photograph.
Okay.
That is a beautiful photograph. Yeah, Hubble photograph.
If it's, so how do we see the star in the middle if it's dark?
That's a galaxy. So this is actually a huge massive galaxy.
Okay.
And we can only see the light from the stars, but really the fact that all of those stars came together in this big galaxy is from the gravity that is mostly from the dark matter. So here you have like light tracing mass. I see a very bright, massive galaxy has lots of stars in it, and that tells me that there's a much more massive dark matter, what we call dark matter halo there as well.
In between.
The stars in this galaxy are living in that dark matter halo. Yeah, so every galaxy you see, you just see the kind of normal matter that sinks to the center, but there's a much more extended dark matter halo that really is what, I mean, that the gravity of that is what pulled everything together.
So the situation is kind of like this. Imagine that this is the blue light emitting galaxy. There's a big galaxy here, which is the yellow. And then Tesla is the Hubble Space Telescope observing this light.
Oh yeah,
so the light
right,
gets bent by
Around
it,
Okay.
and it converges back in there. But the key thing, and why this is relevant for dark matter, is that you can estimate the features of this ring, the Einstein ring, based on how much matter this yellow galaxy contains here in the middle.
Right.
And in this way, you can compare the visible matter with the invisible matter.
Yeah.
And estimate exactly how much of the matter is not visible.
Yeah,
It's
so
a
this
direct measurement of the amount of dark
the
matter.
lensing, okay.
May I ask an extremely simple question? So are you saying dark matter is unevenly distributed?
Yeah, it clumps just like so if you see this is a simulation. If you see my cosmic web, imagine this would be the dark matter distribution. It would look very much like that filamentary thing. And then actually, if I go all the way back to my intro, so this is another simulation. You see the black is the dark matter. You see this huge filamentary thing. And then you can paint on galaxies in those denser regions. Those are the brighter things.
This web system is dark matter?
Dark matter, and then you can see it also in the distribution of galaxies. Galaxies are not evenly distributed either.
No, I see the
Yeah.
galaxies, but they're white.
Yeah, so the stuff we see is it's a bias tracer, but it's a tracer of where the dark matter is.
I guess
Yeah.
that raised the question is that, is there a ratio of ordinary matter to dark matter kind of constant wherever?
That's a
actually
great question.
Let me come back. I have a slide, and we'll come back to that. It depends on the size of the system, really, like how it's not completely constant, no, but we can probe it through. Yeah. So.
You'll get to that.
Yeah, what did I want to say? I wanted to say, yeah, so the lensing here tells you how much that's due to gravity. So it tells you how much gravity there was. And like Stefano said, you can add up what the stars would have contributed and see that there's something else, needs to be something else there.
It's one way to measure the
One-
mass to light ratio that you were.
One way, yeah. Okay, so the very first evidence of dark matter actually did come from clusters of galaxies. From Fritz Zwicky, observing the Coma cluster. So this is a Coma cluster of galaxies. You can see two large galaxies, but pretty much all of the galaxies you see in this field are part of this cluster. And so Zwicky just had his, this is 1933, just had his visual light observations. And what he could look at was the orbits of galaxies. These are moving within the cluster. He could look at the orbits of galaxies and based on how fast they were orbiting, use that gravitational effect to say how much mass was there. But then you can count up all of the galaxies and some understanding of like what stars are in galaxies. And he concluded that the galaxy, there needed to be 400 times more mass than what he was seeing in the galaxies themselves. So, and this is just a slide to say, this is really just pretty simple gravitational argument, just like, the Earth going around the sun, right? So the speed with which the Earth orbits the sun depends on the mass of the sun, right? And the distance. But in that same way, this is a different cluster. You can see some lensing here, which is pretty cool. So in the same way, using actually redshifts, for those who know what those are, Zwicky was able to look at like how fast the galaxies were moving relative to each other, orbiting in this system. And that tells you how much mass needs to be there. And it was much less than what was in the galaxies. And then, so that was the first evidence, but really didn't gain traction until later when, in particular, Vera Rubin and Kent Ford, and then repeated by others, looked at the rotations of galaxies. So again, this is a gravitational argument. Pretty much all of our evidence for dark matter, I guess exclusively is gravitational in one way or another. So you imagine this big galaxy and it's rotating. Right? So again, just orbital mechanics. And so you have a star that's rotating at some speed. And so what you'd expect is if there was just the stars and not anything else, that if you looked at the rotational speed as a function of distance, yeah, that at first it would grow. And then when you got outside of where there were really any stars, if that was all your mass, it would start to trail off. And what they saw, this is the data. So what you observe is that it continued to grow. And so that says that there's first of all, a lot more mass than what's in the stars. And second of all, it's distributed on much larger scales. It's much more diffuse than where you see the stars. The stars really just sink to the center and the dark matter halo is much bigger. Okay, so this was really, were some of the observations that made people really start paying attention to this dark matter story. And this is an aside, this is not on dark matter, but well, it's I guess a form of dark matter, is to say the same kind of gravitational arguments was what was used to show that there has to be a black hole at the center of our Milky Way galaxy. So this is a Nobel Prize in 2020, at least the observational half went for, here's a little movie, it'll play. So these are like, they traced over years the orbits of individual stars. Look how close that one gets around the center of our galaxy. And you see how close they get, right? And so it's the orbital speeds and the fact that they get so close and you don't see anything. There has to be a lot of mass in like a teeny tiny little region that basically can't be anything other than a black hole, because if you cram that much mass into such a small region, it naturally collapses to a singularity.
Okay.
Yeah.
So those stars are moving very quickly.
Yeah.
They're stars moving nearly the speed of light.
No, not at all.
0.4 or something like that.
I guess I don't know off the top. I don't know what but I don't think it's that fast.
I
but
was
they're
amazed.
yeah,
Yeah.
but they are. I mean, this was I mean, again, it's nice that the universe gave us stars that like in a few years did a complete orbit that we could actually track over time. So they've been doing this for, I want to say more than 20 years, 30 years now, but yeah, so similar kind of arguments that show that there's a black hole at the center of our galaxy. All right, so that's just kind of an aside. Okay, so there's mass we're not seeing. The first question you might ask yourself is, okay, just because I don't see it doesn't mean it's not perfectly normal stuff, right? I don't see black holes. I don't even see like neutron stars or planets or anything that's not fusing to give light. Yeah. So, okay, maybe it's ordinary matter that's just not, lighting up. And in fact, if you take Zwicky's picture, this is Zwicky's, not Zwicky's literal picture, but what Zwicky would have seen in visual light of the coma cluster. And then if you look at, so I started my PhD work in X-ray astronomy. I've kind of wandered over the whole electromagnetic spectrum now, but this is the coma cluster seen in X-ray. So much more energetic, shorter wavelength light. And what you observe in X-rays is actually between those galaxies, so filling that region between the galaxies is very hot. I'm going to call it gas. It's really very ionized plasma because the gravity in these clusters is so much that like the ordinary matter that falls into it gets heated to like 10 to the 8 Kelvin, like super hot. And so once you put on your X-ray glasses, you can see. So here's a bunch of ordinary matter that we were previously missing. Okay, fine. So X-ray observations can actually give you another gravitational handle on what the total mass is, because that the gas pressure balances the gravitational attraction in the cluster. And so using those X-ray observations, you can estimate the total mass of the cluster, and you can also add up how much gas, like how much of the ordinary matter is in that hot component. And what you find is that about 2% of the mass is in stars, 13% of the mass is in that hot gas. Okay. So still only 15% of the mass that you think is there is in ordinary matter. And so 85% of the mass then has to be in something else, and that's the dark matter. And so I had an earlier question about, whether that ratio of ordinary to dark matter was constant. So clusters of galaxies, they form out of such, the original in the early universe region of space that then pulled together to make that cluster was large enough that they are pretty, they reflect pretty well the overall composition of the universe. Smaller structures, not necessarily, because you have to, if you think about like the time it takes to escape from some region of space, for smaller objects, that's small enough that you can get biases. But clusters form out of such large regions that you can do a very simple calculation of over the time of the universe, if anything could have appreciably gotten out, and it can't. Yeah.
So is all the hot matter in stars?
No, this is actually really a diffuse soup, a very hot diffuse soup in which the galaxies are living and orbiting.
But like between us and Andromeda, is there any hot?
That is not, we are in a much smaller structure called a group. It's a local group with us, Andromeda, and a bunch of dwarf galaxies. And yes, there is, it's not as hot because of.
We keep hearing the universe, the space is 2.7 degrees Kelvin.
Oh, empty space, yes, but not inside the structure. So between us and Andromeda, there would be something I would call warm. It's a smaller dark matter structure. And so I showed the cosmic web, the filaments, those are traced out by dark matter, but there is actually also gas at a variety of temps. So the larger the structure, the hotter it would be, but there is what's called the WIM, the warm intergalactic, warm hot intergalactic medium. Yeah. So
that's a very good
yeah,
observation.
Yeah.
You just don't see it because it's too cold to shine in X-rays.
Yeah, too cold for X-rays. You can go to like UV. We have some colleagues at Santa Cruz that look at other wavelengths and see that. But yeah, it's there. Just yeah. Okay. And this is just to say, so this is one argument for the kind of that pie chart, at least of the mass component that I showed. But you can come to similar conclusions from observations of the cosmic microwave background. Also, it turns out the abundance of the very light elements that get made in the early universe tells you about how much ordinary matter there is. Those are a little bit detailed. I won't get into them. All I want to make is the point I want to make is that there's multiple ways in which we can add up all of the like ordinary matter, and it definitely isn't the total mass. Yeah.
And these smaller structures where you can get escape, does that give you a higher or lower ratio?
In general, so at the centers of galaxies, for example, you know, where all of the stars live, those can be, I won't use the technical, those can be dominated by ordinary matter. Like the center of a galaxy, the mass in stars at the center of our galaxy, for example, is
Not the
as
very center, but you mean just
in general where most of, yeah, in general where most of the light is, in galaxies, the fraction of ordinary matter is higher than the overall universe. It sinks more easily because it has different forces on itself. It sinks more easily than dark matter.
So more or less, the picture is the following. On very, very, very large scales, like these clusters of galaxies, you have a ratio of dark matter to normal matter that is pretty much the same as the universe as a whole. And then you get to smaller scale, like the Milky Way around galaxy. And there, at the periphery of the Milky Way, pretty much the same ratio as everywhere else. As you get farther inwards, there's increasingly more ordinary matter than dark matter. And I'll actually have a question for the audience during my part of the talk, where we compare how much ordinary versus dark matter there is on Earth. And it's unbelievable. There's very little dark matter around. But as you keep going to smaller scales, at some point you don't have enough mass to actually form stars. And so the smallest galaxies are back again, dark matter dominated. So you're kind of dark matter dominated, ordinary matter.
Yeah, dwarfs and clusters are great probes of dark matter because they're dark matter dominated, and then the galaxies in the middle are not. Can people on Zoom actually hear Stefano when he's okay? And I do encourage if people on Zoom want to like interrupt for questions as well. Okay, so fine, it's not ordinary matter. And this is one of my favorite ex-KCD comics, Department of Astrophysics motto. Yes, everybody has already had the idea, maybe there's no dark matter and gravity just works differently on large scales. It sounds good, but it doesn't really fit the data, which is true. But this is the next, well, one of the other obvious questions you might ask is, okay, we have the scales on which we've tested laws of gravity, general relativity, but maybe on the scale of the universe, something, or, you know, of these large structures, we need to modify the laws of gravity. We don't actually need something new. Because obviously everything I've talked about is gravitational evidence. So there's a variety of reasons that that doesn't quite work, but I think one of the clearest is actually that growth of structure. So the top here are, you know, snapshots of that simulation that I showed earlier. And so we actually see that in the real data. So this is the, you know, the cosmic microwave background that I talked about, circa 380,000 years after the Big Bang. And then we live today, 13.8 billion years. It doesn't show up as well in this projector, but this is not even the largest galaxy survey we have now, but this is the Sloan Digital Sky Survey, and every little point is a galaxy surveyed. And in the locations of those galaxies, you can visually see that cosmic web of structure traced out by where galaxies live. So that structure 13.8 billion years after the Big Bang. And so, you know, the trick is having a cosmological model, dark matter, dark energy, and everything that takes this to this. And in particular, this is like, you know, if you ever see the like popular science articles showing the cosmic microwave background, the picture I have here is very like what you would see, but that's not actually what the cosmic microwave background looks like. What it looks like is this. It is almost exactly the same everywhere. So much almost exactly the same that like, so you subtract it off and you get this picture, and, you know, you get little hotter, denser regions and little cooler, less dense regions. But those differences are 1 part in 10 to the 5. So really almost exactly the same. And then you go forward to today, and clusters of galaxies they have, compared to the kind of average density universe, density contrasts of 1,000 or more, right? So I have to take things that started at an overdensity of 10 to the minus 5 and take them to an overdensity of 1,000 in that amount of cosmological time. And the thing is that if we didn't have the dark matter, we wouldn't be able to do that quickly enough. And that's because, you know, before the cosmic microwave background, all of that ordinary matter was in this, you know, kind of plasma soup, and it wasn't clumping together until the universe became neutral at the era of the cosmic microwave background. And then it can start clumping, but it doesn't have enough. If there's no dark matter, it doesn't have enough time. So what you need is that dark matter starts clumping earlier. So it sets up the clumping such that you can then, from 380,000 years to 13.8 billion, grow structures as we see them today, as overdense as we see them today. Yeah.
So what causes clumping of dark matter? I think
Gravity.
that's the only thing.
Pretty well, as far as we know, you know, some of the candidates for dark matter that kind of like general things you can ask today about dark matter are, you know, it doesn't interact with, you know, our like fundamental, like electromagnetism, strong force, those things, but maybe it has a new force that acts on itself, and that would change structure formation. So we don't know. I mean, it can have some properties that we don't know yet because we just don't know what the dark matter is. But in general, as far as we know, just gravity so far for dark matter. You want to add to?
Yeah, I mean, you pose a very good question. Why initially should I have any density perturbation? And the reason is quantum mechanics.
Yeah.
So
Well,
in a very early universe, you know, and any sort of quantum mechanical field would have some inhomogeneity. And it's those tiny quantum mechanical fluctuations that are bound to exist because of quantum mechanics in the early universe.
Yeah.
That originate those small density fluctuations that we see in the CMB. And then, you know, from the CMB on, we kind of know how to turn the crank. But those initial fluctuations are really quantum mechanical when the universe was more quantum mechanical, which is in the very, very early times.
Yeah. Sorry. If you ask like why were there any perturbations in density to begin with? That gets set up during inflation in the very early universe, as Stefano said. In terms of like why the dark matter then, you know, clumps, it's basically, you know, gravity. You set up some region that's a little denser, and then it naturally pulls together because of gravity. Yeah. Okay, so it's not ordinary matter. We can't just simply adjust gravity. So other questions you can ask is how much dark matter is there? And you can get that from structure formation. This is an example of clusters. So, you know, in a model with less dark matter or a model with a lot of dark matter, and time goes this way. So earlier, and all the little circles are clusters. So earlier evolving to today, and you get, depending on how much matter is there, you get different evolution histories. And that makes sense, right? Because the amount of mass is going to tell you how quickly things are going to pull together through gravitational effects. If you look, it's a little subtle. Why do you start out with, why does this early time less dark matter have more clusters? It's because, you know, we see what we see today. You have to run it backwards, right? And so you run it backwards. So what happens is if there's less dark matter, things pull together slower. And so you have to start with more. So it means actually those initial perturbations have to start out bigger. But that's just to say that, you know, looking at, you know, benchmarking, like how many clusters do I see in some volume today? And how many clusters did I see in some, these large structures? How many did I see in some similar volume earlier in time? That evolution is very much tied to how much mass is in the universe. Okay, so you can also ask what kind of particle is it? And again, structure formation can tell you a lot about this. So early on, generically, there were two possibilities. There are the possibilities where you have so-called hot dark matter. So this would be a very light particle that would be moving relativistically. And in fact, we have a particle like that, the neutrino, and Stefano is going to talk about that. And then there's another, on the other end of the spectrum, there's maybe it's a very massive particle, would be slow moving, and there's candidates for that as well. And all I want to say about that is that the way that structure forms in those models is fundamentally different. In the hot dark matter picture, you form, largest structures first and then they fragment, versus in the cold dark matter picture, you form the smallest things first and then they gradually clump together to make bigger and bigger things. So given the movies I've already shown you, you can easily guess that this is where we are. So it can't have been in the early universe, dark matter can't have been relative, it has to be sub-relativistic early enough, basically, is what that history of structure formation tells you. And I just want to point out that, Joel, along with George Blumenthal and Sandy Faber, were the originators of this cold dark matter paradigm that really is where we are today as like the kind of best general picture of the kind of dark matter we have. Okay, so the history of structure formation tells us how much dark matter there is in the universe. It's about 25% of that energy density. It also can tell us other things about the dark matter. So for example, dark matter can't be too fast. That's what I just said. At most, it can be warm in that hot, cold picture. It can't be too light. And I think Stefano will talk about this some. So there's also, based on the sizes of the smallest structures that we form, it can't be too small either. And it can't push on itself too much. That said, there could be still some dark matter force or forces that we don't know about. So all of these things we have only limits on, we can't rule them out, but they are things that we can study based on structure formation, based on the shapes and sizes of structures that we see. So again, these have gravitational consequences, all of them, that we can look for.
Are you going to be saying more about those things? Like, I think I kind of understand what you mean by not too fast. I don't really understand what the logic is on the too light.
I'll talk.
I'm kind of saving. So Stefano's going to tell you about some of his like favorite 4 current dark matter candidates. So I'm saving some of that for him.
But it has to do with quantum mechanics.
Yeah.
And that's very principle.
Yes. Well, basically, if it's too light, the wavelength of that particle is like becomes the scale of a galaxy, and then you'd like have galaxies that look, wave-like instead of like, galaxy-like.
But you guys live with all sorts of crazy ideas.
Yes.
Yes, in fact, but what is it? This is another joke. I love XKCD. I don't know if you know it, but what is it? There's literally 90 orders of magnitude in mass in terms of what the dark matter could be. So there's still a lot. We know a lot about it, but there's still a lot of possibilities. Some of these are real and some of these are jokes. Axions are real, sterile neutrinos, black holes, Stefano will talk about. Bees and space cows, not so much real candidates. But this is just to show you that really, literally, the dark matter candidates span 90 orders of magnitude in mass. So how can we learn more about it? There's 3 basic ways of going about that. First is so-called direct detection. So this is like not really an experiment in a lab. It's more like a giant experiment in a mine underground to reduce backgrounds, but a terrestrial experiment where you're essentially looking at, there's dark matter all around us, and you're looking at the scattering of dark matter off of normal matter, okay? We could also hope with our accelerators like the Large Hadron Collider to produce dark matter. Yeah, if we have enough energy, maybe we can produce dark matter. We wouldn't really see it. What we'd see it is like missing energy. The energy you put in, and then you wouldn't get it all back out again. So we might be able to make a dark matter particle. The one that we primarily work on is called indirect detection. So that's astrophysical signals from dark matter. We don't know what it is, but we know where it is because of its gravitational effects. And depending on the candidate, there's a lot of signals you can look for, and you can also play these games on using those gravitational signatures to tell you more about the general properties of the dark matter particle. So yeah, that's just to say this is primarily where we are. And I'm not going to go into this in detail because Stefano is going to talk about some actual candidates for dark matter. But being an observer, I just want to highlight the electromagnetic spectrum. So everything, wavelengths in the very high energy gamma rays from the size of like nuclei of atoms up to radio waves the size of buildings. And all of these, depending on what candidate you're looking for, you know, which type of dark matter you're looking for, give us ways of trying to understand dark matter, or at least, you know, rule out some of those 90 orders of magnitude of candidates. And I think actually something that's quite unique about our work is that we have been very broad-minded in looking for, we've used everything from gamma ray, X-ray, visible, radio, to try to understand more and broad-minded in the types of dark matter that we look for. So I won't say more about this. And so this is just two examples. And also I wanted to highlight with these two examples of some of our work, something that I think is really great. The universe is pretty kind to us, in fact, because it turns out that generically, because sometimes signals come around that people like to think are maybe signatures of dark matter. So for example, an excess of gamma rays from the center of our galaxy, which is very dark matter dense. And the thing is that we have a lot of dark matter structures around. And so if you see a signal from one place, you generically predict that you would see it in other places as well. So for example, so I don't know if you can see these little curves here. These are like dark matter models fitting the gamma ray excess from the center of the galaxy. But we have near us, Stefano mentioned that the smallest galaxies, dwarfs, are very dark matter overdense, and we have some of them very nearby orbiting our Milky Way. And given the dark matter densities, generically, if you see something from the galactic center, you would have expected a gamma ray signal from those dwarf galaxies as well, which we do not see. And so non-detection rules things out. And so this is an example of using the Fermi Gamma Ray Space Telescope observations of dwarfs. And you can see that the non-detection of dwarfs puts a lot of pressure on the possible dark matter interpretation of that galactic center signal. The other thing that's really wonderful is that, I mean, it depends on what candidate you're looking for, but in a lot of cases, if you see something at one wavelength, like gamma rays, then you expect signals at other wavelengths as well. So this is an example of a project we did with a former PhD student where there was a gamma ray signal from the Andromeda galaxy. That's the nearest massive galaxy to us. And, you know, one of the possibilities is that's dark matter. So you have dark matter models that fit the gamma ray signal. And what you find is they predict a signal in radio. So really like long wavelength light that is, if that was dark matter, would be brighter than what we actually see. So there's a lot of ways we can go about testing any possible signature. Oops, and I said, so this is just to say, so we actually started working together kind of on like the generic WIMP, weakly interacting massive particle type of dark matter in X-ray and gamma ray. So this is like, we were really fortunate when we first came to Santa Cruz. We arrived just before the Fermi Gamma Ray Space Telescope launch. So you can pick out like very young versions of ourselves in this picture with the Fermi group. So we were fortunate enough, we got to lead papers really with the very early Fermi data on using clusters and dwarfs to look for dark matter signatures. And then, as I said, we've meandered around the electromagnetic spectrum. So this gamma ray radio work was done by a couple. We've also been able to share graduate students where they get, you know, some of the theoretical side, but also the data analysis side. So we've had kind of two joint graduate students to date that have worked on, you know, combining the gamma ray and radio. And I think I actually got both of them into X-ray at some point as well. So these are some examples of some of the stuff that we've done together. And that's it for me. So these are just some fun pictures. We haven't gotten to get together in person that much recently, but this was a recent picture of my group at a party for one of our PhD students that graduated. So Stefano, I know, also has pictures. We, both of us, I mean, we work with graduate students, of course, but we both also really enjoy working with undergraduate students. So both of our research groups have a lot of undergraduate students in them. And, you know, this is me with our kids looking at the last solar eclipse. And my graduate student with one of the telescopes we've been using for a survey, the dark energy survey I didn't talk about, but yeah. And then I won't talk about these, but if, since sports was mentioned, here's some swimming photos and you can ask me about those later if you want. Okay, so that is it from me. And I will then get up Stefano's talk. Does anybody want to, especially on Zoom, where you didn't get to ask questions before? Anybody, any questions in the meantime? You want to?
Any Zoom questions? Raise your hands on the pictures here.
Hang on, gotta.
I have a sort of tangential question.
Okay.
So about a third of the nation thinks that the universe is 6,000 to 10,000 years old, and there's a whole bunch of ways like carbon dating and geological strata and foraminifera on the thing and redshifts. Is there any? There's several at the the astronomical scale too, like redshifts and the cooling of the universe. Is there any like so simple that 99% of people could grok it? Evidence that you've come across that says, nah, it's probably a lot older than 10,000 years.
Well, I mean, if you're not going to believe the fossils and the like dating of the early rocks, I don't. I mean, what are I
don't know.
I don't know. I mean, yeah.
There's got to be something.
I mean, obviously, you can talk about like light travel time and stuff,
Yeah.
but if I don't know. I mean, if they're,
that's even harder than fossils. I
yeah,
think.
exactly. I don't know. Yeah.
Actually, something that always bothers me is with these huge numbers we have, the numbers of stars and galaxies, et cetera. Seems to me that 14 billion years just isn't long enough.
And that's actually one line of evidence for the dark matter.
Yeah.
So the universe is very young. If there weren't dark matter around, the universe should have been a lot older than it is. So
To make what we see today. Yeah. Yeah.
But yeah, when I talk about our cosmological model, I always point out that humans have been trying to make sense of the cosmos forever, right? Ancient Chinese, Mayan civilizations, everybody had their own cosmological model. So what sets ours apart? And I think the key thing is that the modern cosmological model is a scientific theory, which technically means it makes predictions that can falsify it, that can show it to be wrong. And the modern cosmological model makes a lot of predictions that can kill it. No ancient cosmology ever made predictions that would enable people to falsify those models.
Yeah.
But even the modern cosmology, so like one of the things is this turtles all the way down.
Yeah.
And before 13.8 billion years ago, it's turtles all the way down.
Yeah, well, I mean, even on the dark matter side, on my like electromagnetic spectrum, one of the things is, I mean, we have that 90 orders of magnitude to play with, but really it's hard. It's actually hard now to invent a new dark matter candidate. I mean, because of all of the constraints we have, one of which was I had on my slide, don't mess up the CMB. You can't mess up the early structure that we see. And that actually is pretty constraining. But just if you really want to blow your mind on terms of like what's there, the Dark Energy Survey, which I'm part of, was a 6-year survey using a telescope in Chile. We have surveyed something like 400 million galaxies.
Wow.
Over the last 8-ish billion years. Oh yeah. So yeah, there's a lot. Yeah, I know. Yeah.
That's terrific. Thank you so much.
Okay. I will turn it over.
Right. So thanks again for having us today. It's so much fun. So yeah, I thought I'd start by just putting myself on a map. So we're talking, I forget your name. Hugh. I was talking with Hugh about, where I grew up, and I'm from northwestern Italy. So you see, this is France and Switzerland. I'm, much closer to France and Switzerland than I am to Rome over there. So this is an ancient picture of my family in the Alps. I spent pretty much all of my summers and winters near Mont Blanc here. That's me. right there. That's my father when he was, I think, 20 or 25 years younger than me. But anyways, this is the current snapshot of the family back at my parents' house a few years back. Yeah, these are our two kids, and that's a more recent version of my dad. Anyways, this is my younger brother, who's a fantastic mechanical engineer. He worked for Ferrari for many years. He actually was the guy who sort of erred on the side of putting an automatic gearbox on Ferrari for the first time, but you know, I cannot forgive him for it. and guess what the Ferrari model was named? Ferrari California. Yeah, the dual clutch system. So anyways, he's very Catholic, so he has I think at the moment 7 kids, but he keeps going.
I think that's missing one.
So you know, I'm Italian, and I was telling Hugh that my alma mater is Pisa, and perhaps the best known Italian physicist from Pisa University is Enrico Fermi. And I mentioned Fermi because he came up with this weird name, neutrino. If you know some Italian, you know that ino means small, smaller, right? So what Fermi noticed was that, you know, in nuclear processes, there was some energy that was carried away that wasn't visible. And so, you know, the only neutral particle at that point was the neutron, but these were clearly much lighter, much thinner. And so Fermi called them neutrino, the small neutrons. The reason why I'm bringing this up is that neutrinos are actually part of the dark matter. We know almost exactly how much of the dark matter is made of neutrinos, and that's about 1%. So neutrinos are the 1% of the dark matter. But of course, you know, we're in Santa Cruz, so we are the 99%. We care about the 99%. And that is something we fundamentally don't know about at all. So what 99% of, you know, this key ingredient, as Tesla was pointing out, of the universe of our modern cosmological model, we don't know what it is. So here's my question for you all, and Joel, you cannot answer, so sorry about that. We said that, you know, the ordinary matter to dark matter ratio changes depending on where we look, but think about the volume of the Earth. All right, that's a large volume, and guess how much dark matter is contained in the volume of the Earth. And I'm going to give you 3 possibilities: as much as an asteroid mass, as much as the moon, or as much as a squirrel.
I'm going with the squirrel.
Yeah, because that's.
I vote for the squirrel.
That's a mind-blowing one, and it is. It is a squirrel. There is a squirrel worth of mass, almost exactly, in the volume of the Earth locally. So locally, we are in a hugely overdense ordinary matter region. And it's sort of, yes.
Would it be fair to say that Newton's laws are off by 1 squirrel?
Newton's laws work pretty well. I mean,
yeah, that's
they're
what I'm
part
saying,
of,
1 squirrel wrong.
So, you know, there's not a lot of dark matter around us. And of course, you know, another XKCD joke seems to be the thread today. Dark matter is in squirrels, but if you put it in the numbers, you know, in terms of mass, it means the Earth contains 1 squirrel worth of dark matter. Wow, is there any way to find out which squirrel it is? No, it's not literally. Oh, that explains why they weigh enough to set off the spinning bird feeder. So dark matter is in squirrels. And today, I thought I'd share with you, you know, I've worked in this line of business for 25 years. And actually, maybe I'll say a couple of words of why I started working on dark matter. So, you know, when I was in college, I thought that all the smartest guys were doing string theory. And I thought very highly of myself. So I'm like, okay, I'm going to do string theory. And so I was working on these really weird theories where, you know, like space directions don't commute and really weird stuff. But I didn't like it. So at the end of college, you know, I got into graduate school, and I hated physics. So I'm like, okay, I'm gonna do management consulting. So I did that. So I did that, but it was 2001, and I got into management consulting right after September 11. And so at every major firm that was hiring management consulting people, they were hired to fire, folks. And so it's really miserable. And I got back, and I, like every good Italian boy, I went to my family, like, I don't know if I want to be a physicist. And so we had a family friend who was working at CERN, and my grandmother told me, okay, talk with my cousin, who's this particle physicist, and see what he says. And he told me, you should work on astroparticle physics, because there's a lot of stuff we don't know, and you're a smart kid, so, go into that field. And sure enough, I followed his advice, and it was a great time to, think about really understanding what the dark matter was and is. And I've been in that line of business ever since. It's been a lot of fun, and I really fell back in love with physics. I went back to graduate school, and then after that, I moved to the US, and I was at Caltech, and I married Tesla shortly thereafter, and that's history. But anyways, back to the
No more management consulting.
no more management consulting. I keep telling my student, a lot of them, they go and work for Google, for Apple, or whatever, and they're happy. I think, it was kind of an accident of the time I went to management consulting, maybe, but ultimately I think it was a blessing, because I really love my job.
Have you been department chairman yet?
So Barry, let me tell you what I am.
This is a survivor.
I am chair of the Committee on Academic Personnel, which is much worse.
I did that.
You've been there.
I did that.
Barry and I were sitting together in a committee of faculty welfare a few years back, but I didn't have enough, and so they wanted me to get in line to become Senate chair. I'm like, nope, that's I draw the line at.
That's really into the dark side there. Okay.
So I'm an associate director of SCIP, but that means it's like, the title without all of the
Yeah.
pain, so
But anyways,
we'll
no,
see.
I still love my job anyways, even if. So the first candidate is what Tessa was mentioning, this wave dark matter. So the idea is the following. Maybe the dark matter, we don't see it because it's a very, very light particle that is very diffuse. It's kind of like a wave. And, we have no way of seeing it because we're deep in a quantum regime where this particle behaves like a wave and not like a particle. All right. And the interesting thing is that there is an absolute lower limit to how small the particle that makes up the dark matter can be. And as Cesar was mentioning, that limit corresponds to the wavelength of that particle being maximally as large as the size of dark matter halos we observe. And the smallest dark matter halos we observe are things that host this type of stellar populations, that are dwarf galaxies. These are about 100 million times the mass of the sun. So they're still pretty big. There's a few stars in there. So what you cannot have is the wavelength of the dark matter be larger than the size of these galaxies. Because if it were, quantum pressure would counteract gravity and would not allow you to form these galaxies. These galaxies would not exist. So it seems preposterous, but actually, back to string theory. String theory predicts a lot of these type of particles should exist. And string theory is very probably wrong, but the general framework that very light particles should be around is a pretty firm predictions of any theory of quantum gravity. So there's a lot of reasons to believe that this has some bearing on reality. And in fact, the inventor of perhaps the most compelling wave dark matter candidate is Michael Dine, former department chair in physics and now emeritus. Michael is a fantastic guy, and he came up with the axion as a dark matter candidate.
By the way, actually, a lot of the dark matter candidates come about because there's other problems in particle physics. So this one has to do with a difficulty, an in the strong force, basically, but creates this light particle that could also potentially be the dark matter.
Yeah. So we always like to kill multiple birds with one stone.
Yeah.
Possible.
These birds are surviving.
Yeah.
Yeah.
Well, they can still be there and solve like this, the so-called the strong force problem, but not be the dark matter. It
Yeah.
depends on their properties, right?
Yeah.
Yeah.
They not necessarily are connected, but they could.
They could-
And so these are folks in the astronomy department that that have done some work and are continuing to sort of look for this type of dark matter candidates by looking at where these stars are within these dwarf galaxies. Because again, if you have some quantum mechanical effect, you're expecting that the dark matter density at the center be pretty flat because you cannot clump, again, because of quantum pressure. And so, you make predictions that you can test by just measuring where stars are. So that's one way, one sort of indirect way to see whether the dark matter is this very, very light particle. And actually, one of our postdocs in the theory group is currently one of the leaders in the world in trying to think about other ways in the lab to capture these very light dark matter candidates.
Like tuning a radio to detect really light, like dark photons.
Yeah. So one idea is, sort of, since this is a very long wavelength type signal, kind of like radio waves, then why not building a radio, a dark matter radio that would detect the dark matter if tuned at the right frequency? And so you can actually do that. Because
This is much larger than radio wave, though, right?
much larger than radio radio.
That seems like a very hard radio to build.
Yes, but you can.
Wow.
You can, nonetheless. You don't, radios are much shorter than radio wavelengths, right? So you don't need to build huge radios to detect very long
Actually,
wavelengths.
But do you need a satellite? Because the longest wavelength radio waves reflect off of the ionosphere. They
Yeah.
don't actually come down.
Yeah.
So do you need a satellite? For
So
this, or-
these are not electromagnetic wave.
Oh, yeah.
So
I'm being
that would be
silly
fine.
here.
Yeah,
Yeah,
that would-
I'm being very silly.
But some people do think about putting a dark matter radio on the moon. So yeah, there's also some crazy ideas there. So here's my second candidate. My second candidate is sort of at the complete other end of the spectrum. When you think about dark stuff, there's nothing really darker than black holes, is there? So the question is, can black holes be the dark matter? And the answer is no, because black holes that we know and love form exactly from the collapse of stars. But as Tesla explained very well, there's a lot more dark matter than there are stars. And so, since only a fraction of stars end up producing black holes, that's not enough. However, let's go back here to those quantum fluctuations in the early universe.
Right.
So if those fluctuations were large enough that, that you would shrink enough density of energy and mass in the very early universe to create black holes, then those black holes will still stick around and wouldn't need stars to form. So instead of having the collapse of stars, you would have the collapse of space-time if you had large enough density fluctuations in the very early universe. So that's an old idea that, in fact, Stephen Hawking back in the day had. These are called primordial black holes. They're primordial because they don't form from stars, but rather it's just the clumpiness of space-time in the very early universe that could have produced them. So we know that they cannot be too massive, because if they were too massive, if you look at galaxies like this with these beautiful flat disks, and you imagine throwing a giant bullet, you would warp the disks kind of like this almost immediately. So if the dark matter was too massive, you would disrupt the stability of disks. You would also sort of punch through these dwarf galaxies or globular clusters and disrupt them, sort of like imagine a bullet going through. Just the effect of gravity would pull stars along. So we have an upper limit. These primordial black holes cannot be too massive, but if they have the mass of, say, an asteroid or so, they could totally be the dark matter. So it's been a very exciting time in the physics of black holes. One of the reasons is that we've imaged directly a black hole, a very massive black hole that cannot be the dark matter. This is a black hole in the center of a massive nearby galaxy,
Virgo, yeah.
Virgo. So this black hole is about 1 billion times more massive than the sun. But the fascinating thing is that putting together a bunch of radio telescopes that you see here, people have sort of superimposed radio pictures of the black hole, and they've actually imaged directly the black hole and its surroundings, which is mind-blowing.
What's the mechanism of imaging that?
It's interferometry. So, you know, you have the funny thing is like you'd love to do that in real time. So, you know, you're precisely adding them. What they have to do here, because they're around the world, is record the data with an extraordinarily precise timestamps. And then they actually take the data, fly it on planes and combine it. But you're interfering the waves seen from the same object at different locations. And the length of that baseline, the longer it is, the smaller size you can resolve, right?
So it's
So
kind of like
it's-
having a you know, if this was an optical telescope, it's kind of like having an optical telescope with this size.
Yeah.
And so-
Well, because I mean, you have different direction, you know, because of the offset in position, like you're pointing slightly different directions towards the
So it's
source.
a diffraction effect, sort of?
Yeah, you're literally interfering the waves
Yeah.
from the different locations
very
and
large
then
scale,
given their
yeah.
offsets, yeah.
Cool.
yeah.
And the colors were supplied by your friendly whoever.
The colors are, that's
Yeah,
some
I mean, that's good.
visual,
That's a
yeah.
good color. for a
Some
black.
visual, but it is, you know, from real data.
That's cool.
So the other thing, of course, that you've all heard of is gravitational wave astronomy. And this is, again, you know, here we were talking about Galileo. And I was telling you that there's this Institute of Theoretical Physics in Italy, in Florence, called the Galileo Galilei Institute, that manages Galileo's house in Florence. And so I had the privilege of actually lecturing in Galileo's house.
Yeah.
Just mind-blowing. So of course, you know, Galileo played a big role in the development of physics for a variety of reasons, including that he used a telescope. And here we are sort of the same, you know, equivalent time with gravity waves. So he used a telescope to look for electromagnetic waves. We are starting to look at the universe in gravitational waves, which, going back to Tesla's point that, you know, some electromagnetic waves just don't get to us because they interfere with stuff in the atmosphere. Gravitational waves are great because there's no stopping them. And, you know, so you can see stuff that happen in a very, very early universe, no problem, because there's nothing that stops a gravitational wave. And one of the things that we can do with gravitational waves is look for dark matter. So these primordial black holes would merge sort of like stellar black holes and give off gravitational radiation.
I just wanted to make a point about how incredible these experiments are. So again, you're in the LIGO that you detect the gravity waves. It's an interferometer. It's an interference experiment. Gravity waves are really weak. I mean, you can't stop them, but they're really weak. So what they're looking for, they have, you know, an L-shaped thing, and they're looking for the gravity waves, like changing the
length of the arm.
length of the length. So, you know, so this arm, because of the gravity wave, ends up having a slightly different length than this arm because it's really distorting space. But what they're seeing, what they need to detect, these gravity waves it's basically like changing the difference in length of the arms by the size of an atom. And that's what they're able to see.
One's in Seattle and
And one is
Yeah.
in Louisiana.
But they
And
do
the
it
third
in-
one is in Italy, actually. in
Yeah,
Pisa.
there's a third Virgo, yeah, so there's a third one, but they detected independently in both, so in the arms of both, but then because of you can do a lot when you have the difference in light travel time and that triangulation in terms of knowing where it came from. So that's why the 2 and now the 3 is very important.
Actually, there's a fourth in India, right? That is coming
Um,
online
yeah, I don't know.
shortly. So, you know, but the next step will be to put these things in space.
Lisa.
Because the biggest problem is, you know, the fact that Earth moves and shakes
Yeah.
a lot more than, you know, the size of an atom. And so, you know, seismic noise is the limiter. But if you put stuff in space and shoot lasers in space, you can do much,
As
much
long as
better.
you can fly your.
So as
Your
a
things,
layman, I worry
information,
about
all of that.
signal to noise and errors. And I'm wondering if you're satisfied that we can actually measure this atom's length, that we've tracked all the errors. That seemed like we've done that or not?
Yeah, actually, I think the shifts in the length of the arms, it's much smaller than an atom. I think
Maybe
it's
proton size. It's very small.
yeah.
I have the actual stats somewhere, but
It's a little bit like a 10,000-year-old DNA to me. It's like, you sure you got that right?
So the amazing thing is that nobody would believe that you've got that right if it was seen by one telescope. But when you have 3 telescopes that see exactly the same signal at exactly the same time, 9 time zones apart.
And it's a real ring down, right? It's like a pattern over time that you
Yeah.
can trace. That's
Yeah.
that's pretty unique. I mean, they've actually they put in fake signals to test their system. They had didn't tell people, and they put in like fake gravitational signals to see like if they were
Being
found or
fooled,
not.
yeah.
Didn't we think we found one like a year or two ago or something? Wasn't there was that a false alarm? What was
We
that?
found a lot at this point.
Yeah, so this is the current count of black hole mergers and mergers of black holes with other stuff. So now it's kind of become an established business,
Okay.
and it's we are actually learning a lot of physics. And people have been asking the question, can these black holes maybe be primordial? So maybe they are a part of the dark matter that is substantial. And right. Yeah, so this is, well, I don't know if this movie
But
will
the
play.
bottom plot is you can see the independent but extremely well matching signals from the 2 different detectors, right?
Yeah, so this is, half a second time, and you see these ring downs exactly lined up with an amazing time resolution.
That's cool.
But anyways, the movie's not working here, but so one sort of side story that has to do with Santa Cruz is that this guy, Ryan Foley, and then them with the Dark Energy Survey, 2 minutes later, were the first ones to see light out of gravitational wave event. And so this was presumably a neutron star event that not only produced gravity waves, it also produced light. And this is like billion light years away, okay? And the light came in, within a second of the gravitational wave signal? So, just on time.
Well, actually, the earliest was the Fermi actually saw it in gamma rays, right? Was the earliest pickup of the signal.
Yes,
Yeah.
but this is relevant for dark matter for the following reason, that pretty much any modification of gravity that accounts for dark matter predicts that gravitational waves move at a different speed from the speed of light.
Oh, yeah.
And so in one move, these measurements killed entirely the possibility that dark matter doesn't exist, but it's just gravity working differently. So it is been an amazing feat for the story of what the dark matter is, because it definitely is not.
1 billion years is experimental error.
Yeah, so think about it. A billion.
Yeah, I know, it's very-
Yeah, I mean, it's like 10 to the 9. I mean, it's an incredible precision,
Well,
right?
but
It cannot be an accident.
besides the light, you get a delay mostly because of, you have to start fusing things. Like these are 2 neutron stars, and you start fusing and making heavy elements, and so the light signal actually should have a gap that I think was predicted.
Not the gamma rays, yeah, but
Not the gamma rays, maybe, but yeah.
yeah.
Cool.
So anyways, a lot of my graduate students sensed that gravitational waves is, really a growth field and where the big money is. And so we've been working a lot on using gravitational wave astronomy to look for dark matter in a variety of ways. For instance, one of the things that you can measure with gravitational wave observations is the spin of black holes. So black holes, when a student approaches me and is like, well, I'd like to work on black holes, but it's so complicated. No, black holes are very, very simple. It's the simplest thing. Outside of black hole, a black hole is just defined by its mass and by its spin, pretty much. So it's a super simple object. It's kind of like an elementary particle, right? And so the spin that these primordial black holes should have is completely different from the spin of stellar black holes. In fact, they should have no spin at all if they're collapse of space-time as opposed to collapse of stars.
Have 0 spin?
Right.
How small can they be?
That's a great question. So, and I can tell you exactly. So the smaller a black hole, the hotter it is. So the temperature of black hole is inversely proportional to the mass. And the hotter a black hole, the quicker it evaporates through Hawking evaporation, which is
Oh, okay.
essentially,
Yeah,
you
so
know,
it's primordial. and-
yeah. So a primordial black hole that sticks around up to today has to be massive enough that it hasn't evaporated away.
Yeah, exactly.
And so that amounts to about 10 to the 16 grams, which is around an asteroid's mass. However, you know, if you look at the size, the physical size of a black hole, an asteroid mass, it's, you know, about a fraction of a micrometer. So very, very small object with the mass of an asteroid. And on the upper limit, you can go up to about a stellar mass. So you have, you know, about 10 to the 17 orders of magnitude.
What about Sagittarius A?
Oh,
Yeah, Sagittarius star is about 1 million solar masses. The black hole whose, you know, whose orbits we're looking at.
No, that's not primordial. That's stellar. That's a stellar form black hole. The supermassive ones, I mean, okay, how you get them quickly enough is a real problem in galaxy evolution. But those are from, I mean, you have these very dense regions and you form the earliest stars. They collapse, I mean, they supernova collapse to a black hole. And then you basically, through like what LIGO is seeing, you merge black holes over time. And you grow, and because of gravity, you know, first of all, there's a lot more stuff in the center of the galaxy, but things gravitationally sink as well. So you build up those supermassive black holes out of, you know, normal matter over time.
However, Hugh, you make a good point. You know, some people still question where it started. And in fact, some people do believe that the seeds for the supermassive black holes were primordial.
Yeah,
So
you
that's
have
a
to, you do
possibility.
have to, because it's really hard to make them so big so quickly. So, yeah,
But what
getting
I
them
was
started is,
thinking was that early on in this, when the plasma becomes a neutral.
Yeah.
Mhm.
Becomes atomically, there's plenty of matter and
Yeah.
maybe dark matter around
Yeah.
at that time. And if you create yourself a big black hole, it's got lots to eat.
Yeah. And actually, interestingly, the larger a black hole is, the later it forms. Because roughly speaking, these primordial black holes masses correspond to how much mass there can be within a horizon. And you know from Anthony's class what a horizon is. So you know, the bigger the mass, the later these black holes have to form. So if they are of primordial origin, they form pretty late, maybe, yeah.
but I just want to make a point that the size range he's referring to is the size range if it's going to be the dark matter. It's not that you can't make primordial black holes or other black holes of different sizes, but because of the observational constraints we have, like the bigger, more than a stellar mass, we have micro lensing constraints of, you know, those black holes going in front of stars and lensing the light signal. So that range is, and you have to have enough dark matter. We know how much dark matter there is. We know its distribution. And so we know it can't have decayed away in the lifetime of the universe, so it has to be long lived. So his range is really like black holes that are the dark matter. Black holes outside of that can certainly exist. They're just not the dark matter.
Yeah. So again, this
Okay,
is,
yeah.
unfortunately, I don't think that movie worked. So here's another story where I had a lot, really, you know, I felt so blessed to be married to an astronomer. Was when, you know, people were looking at galaxies in X-rays, and one of the things that could happen is that the dark matter is sort of a radioactive species, so it decays, kind of like any radioactive species, and it produces, you know, some high energy photons, exactly like radioactive nuclei do. And so one possibility is that the dark matter is a heavier brother to the neutrinos that Fermi invented and discovered. And well, whatever. I just read the Italians for nationalistic reasons. So if these stellar neutrinos indeed are the dark matter, then they decay, they produce a normal neutrino and an X-ray photon. And so people have looked at galaxies to see whether they could observe these X-ray photons from the decay of dark matter. And they claimed to have seen a signal. in a bunch of galaxy clusters. So now, here's why I think my wife is so smart,
Mhm.
because I would never be able to pick up these red things, this very noisy data as a signal, but apparently it's a striking signal to an
I
X-ray
never thought-
astronomer.
I want to go on
Okay.
record by saying I never thought that was, knowing the data analysis that has to go in this and what we know and don't know about that data, I never thought it was a striking signal, but that's just my.
However, a lot of attention was given in the community and in the popular press about dark matter being eventually discovered in this 3.5 kilo electron volt X-ray line. And so what we did together was, as she mentioned, the dark matter is the same everywhere. So if these X-rays came from dark matter decay, then any galaxy should produce exactly the same X-rays. And so what we did was, instead of looking at galaxy clusters that, as Tessa was explaining, they have plasma that emits X-rays, so they're very noisy environments. What we did was to look at dwarf galaxies, because dwarf galaxies don't have any gas. They're too light. Coming back to why don't we see X-rays from Andromeda, or which we do between us and Andromeda, because it's too cold and so it doesn't emit X-rays. However, dwarf galaxies are full of dark matter. So if the dark matter radioactively decays, we should see X-ray photons from there. And sure enough, there were none, not at all. And so here's a little bit of history of how this went. The group that discovered the original signal was from Harvard University. And as you know, our mascot here at Santa Cruz is the banana slug. So our rebuttal paper had to do with the fact that this observed X-ray line might come from potassium, which of course bananas are very well known for. So the title of our paper was "Dark Matter Search is Going Bananas." And I can tell you that the Harvard crowd was not pleased with our title at all.
Which we eventually changed.
Well, so eventually we published in the monthly notices of the Royal Astronomical Society, which is another kind of stuck-up place. And so the bananas title was struck down by the Royal Astronomical Society. But still, we thought it was a clever title.
Did it help that one of the instigators of this graduated from MIT?
With the Harvard, yeah.
So anyways, let me move on to the fourth dark matter candidate that Tessa also mentioned. This class of candidates also has a lot to do with Santa Cruz, and I'll explain in a second why. Joel was actually the inventor of supersymmetric dark matter candidates. And for many years, including over a decade of my own work, was dedicated to dark matter candidates known as weakly interacting massive particles. So here the idea is that of the fundamental interactions, the only one that the dark matter can have, besides gravity, is the weak nuclear force. All right, it cannot be strongly interacting, otherwise it would have been very easy to see. It cannot be electromagnetically interacting, because otherwise it wouldn't be dark. So the only thing that it can be charged under is the weak nuclear force. And so for many years, we thought that, WIMPs would be the bulk of the dark matter. And because they had weak nuclear interactions, we could detect them. And people built these ginormous particle detectors, trying to see, as she said already, the scattering of dark matter off of ordinary matter. So, you get a dark matter particle that comes in, it interacts weakly, but it does interact some with normal matter. And you can see the effect of this scattering process in a variety of ways. So millions and millions of dollars were given to build experiments like this, looking for squirrels, but dark matter is neither squirrels nor WIMPs, as far as we can tell today. However, what could have been the case is we just were looking for WIMPs in the wrong place, under the wrong lamppost. And why do I say that? Well, because the amount of energy that you give to normal matter depends on how massive your WIMP is. And so if the WIMP were a bit lighter than what people building these experiments thought, we would have not seen them at all.
That'd be a whip, though, not a wimp.
Well, you know, not as massive particle. Okay, it would still be charged under weak interactions, but just be lighter. Just be lighter. And so these light WIMPs is another place where I think there's going to be a lot of exciting physics. And here at Santa Cruz, we are building up a really strong program in material science. One of the things that people do is they use graphene, which is this amazing material that is sort of a one-dimensional sheet of atoms, right? So these are carbon atoms that literally you can take one sheet apart and just have these super thin materials. And so the idea would be to use these atoms as the stuff that the dark matter would, you know, kick. And the reason why we want to do that is that then you can use these Josephson superconducting junctions to detect very, very tiny energy depositions and go after much lighter dark matter than those other experiments were looking for. And so at some point earlier this year, there was a private donor who promised several $1 million for a game-changing experiment that could revolutionize an entire field. And we put together a proposal. So we'll see if that goes through. But we think, you know, that on the $1 million scale, we might have a chance to go after an entirely new class of dark matter models. So just to sum up, I've talked about wave dark matter that has these puffy halos where quantum mechanics kind of puffs up the dark matter density. These primordial black holes that you can use gravity waves to detect. These radioactive sterile neutrinos that would produce, you know, radioactive photons in X-rays. And finally, WIMPs, but maybe not these massive WIMPs, the little less than massive variety, the lighter variety. And, you know, since Tessa showed some pictures of her group, I thought I'd do the same. We try to be very welcoming to undergraduate students, especially because we think, you know, you got to pass on the enthusiasm to these younger folks. And so my group meetings tend to be a little overcrowded, but these were pre-COVID times anyways. And there's some Prosecco there being opened up for the graduating graduate students. And I thought, since Tessa also showed swimming pictures, you know, I used to be a pack-a-day smoker when I moved to California.
Wow.
And a musician more than a sport.
Sporty, yeah. But, you know, she's a pretty direct person, and she told me, we're not going to have kids unless you quit smoking. And she was very serious, and I knew that. And so I had to find something as addictive as smoking. And for me, that was running. And then, you know, I, like any other runner, I injured my knee and I started biking. And so right now, you know, I'm a lot into triathlons, Ironman and non-Ironman triathlons. And I work with a lot of the kids at the university. You know, I coach both the runners and the cyclists on campus as sort of a, you know, volunteer type position. But it's so much fun. This weekend, in fact, the national championship is going on for triathlons, collegiate, and so I'm you know, crossing my fingers for the slugs to come out well off of the national championship. But it's, yeah, it's been a fun ride, a lot more fun than smoking, to be honest with you. Anyways, thanks so much for your attention.
I have to say, this is a wonderful presentation from two wonderful people, and it was an absolute pleasure to have you here. Thank you so much.
Likewise. I think this is terrific that you guys are organizing this.
When you have, maybe we'll invite you back in a couple of years when you come even closer to discovering.
Right.
Yeah. You know, the field, I think, can move very quickly. You know, we have the tools, we have the observatories. You know, it's just the burden of proof has to be very high.
Yeah.
And so over time, you know, we've, I like to say, debunked a bunch of claims. And in doing so, the cool thing is that you learn a lot of physics that you weren't aware. So, you know, early on when Joel recruited me as a faculty member at UC Santa Cruz, people had observed an excess of anti-electrons in cosmic rays. And, you know, they genuinely thought they had discovered dark matter. And I was one of the first ones to find out what else could have produced those, which are neutron stars. They produce a lot of anti-electrons, and now that's sort of the standard theory for where these extra anti-electrons come from. And I learned a lot in the process of just debunking these claims.
Well, I see Joel's there, and I don't know if he can hear us, but Joel, thank you for bringing this couple to Santa Cruz.
So let me quote Joel. Every time we have, like right now, we have a search for a new professor in the physics department, and every time I quote Joel, I remember, I think it was in my interview to become a faculty member at Santa Cruz that Joel told me, we always hire the best, but we never hire jerks. So
That's good.
That is so important, because you want to be surrounded by nice people that you want to stick around with and do good physics and be friends with. And I think it's extraordinarily important to have that type of environment, because a good researcher is a happy researcher. You cannot have do good work if you're not happy with the environment you're in. And
something we learned at both the science fair and maybe your example is that science isn't a reality TV show where everybody gets kicked off the island. It's a team sport, and
Yeah.
the two of you are
It's really, I always loved astroparticle physics, but I started out mostly on the cosmology side, and that's the part of my work I didn't talk about today. I still do a lot of kind of general cosmology work, but getting to know Stefano, our collaboration started mostly because I think when we were interviewing for jobs, actually, I saw him give a talk, and he had at the time some predictions for what you would see in X-ray from like a dwarf galaxy. And I'm like reading the axis, and I'm like, we could detect those fluxes. And so that's what started it all, was like, and it's been fun. I think he's, like you said, you learn a lot of astrophysics trying to understand these signals that you see, and I've gotten to do a lot more particle physics, so it's been really a lot of fun. And and as you get new capability, like new radio or new capabilities in whatever regime, or you don't find the kind of natural candidate you were originally looking for, I very much enjoy the fact that we get to try a variety of things, like it's a new capability, new wavelength, great, or a new kind of candidate, and think a little creatively about how you would find it.
So do you think the infrared, the James Webb telescope is going to help in that? That's a whole nother spectrum.
yeah,
Infrared, what's useful, well, I think Joel could tell you a lot about JWST observations. What the infrared gets you is, for example, being able to look farther back in time, right, because of the redshifting. So we will get to see the extremely early galaxies and what they looked like, and compared to Joel's wonderful simulations. That's not necessarily directly dark matter, but again, how structure forms, and for example, we see these really massive galaxies really early on, and these really massive black holes, and how you can seed those and make them. And then things like some of the stuff that I'm doing now is more those gravitational signals. So using lensing, for example. And so in general, being able to get outside the atmosphere gives you resolution where you can do things really precise things like lensing, or fainter signals like micro lensing are enabled by some of it. But it's not primarily a dark matter telescope, but that
I'm pretty excited about the Webb telescope when it comes to exoplanets, because ultimately when you look for exoplanets, you're looking for some dark stuff, right? They don't shine,
right.
And so that's great for dark matter, because for instance, if dark matter was a primordial black hole, it would also orbit stars potentially, and we've done quite a bit of work understanding how, if the dark matter is in the form of these primordial black holes, how it would get captured in planetary systems. And so you can translate the Webb's capabilities for exoplanets in searching for these massive dark matter candidates. So that's quite exciting. But then there's a better understanding of where the dark matter is, how it is distributed in galaxies, that might come from Webb as well. So anytime there's new groundbreaking capabilities like gravitational waves, for sure there will be new opportunities to use those capabilities to hunt for dark matter.
So you were talking about using, detecting gravitational waves using lasers in outer space, but how would you be able to,
Yeah.
lock them down tight enough to, I mean,
Yeah.
This is the LISA mission, and it's like a set of, the set of satellites in a very precise formation.
Yeah. So you don't actually need to sort of measure the arm length with that precision.
You just
Because
know where you are.
yeah, so because what you really are doing is sort of looking at the light bouncing back and forth and how the light shifts relative to one another as space-time gets sort of warped by the passage of a gravitational wave. So in practice, I think LISA is going to be placed in these special Lagrangian points where they're very stable points in space, and so so they're not going to sort of orbit around. They're going to be sort of stuck there. These are places where the gravitational attraction for us different bodies gets compensated, and they're stuck there. So I think they're in Lagrangian points where they're going to put them. But the technology has been sort of tested already with much smaller scale. So I mean, it is probably going to happen. I don't know which time scale, but it's the Europeans, so they're much less likely, I think, to flake out than than other countries. But yeah,
Like ours.
that's
Ours, I mean, I think we eventually build the things we set out to build. It's just that, there's a winnowing process of like, you can't build everything. So there's a lot of proposed things that then get studied up to a certain point and then maybe get delayed because James Webb still doesn't launch, or I wouldn't say we flake out, but I do think it takes time, and there's a down selection that happens in what ultimately gets made.
There was the SSC.
There was the SSC.
Oh, yes.
That's
Okay,
exactly
well,
what I was
yes.
going to bring up.
That's true.
So in the
Okay.
case, in the case of the Europeans, it's not one legislative body that can strike down the whole
Yeah, that's true. One political shift.
One political shift, yeah.
I think that's true.
If I could put in a wish list for way in the future,
Uh-huh.
people like Barry do these wonderful courses like on microbiology and food and stuff like that. And someday when you're finished winning swimming awards, raising kids, discovered the dark matter, I would love to see a course that's called a tour of the electromagnetic spectrum. And because that's something that should be better understood by everybody. And it's just so fascinating. You've got very similar physics that underlie it, but all these manifestations from A to Z.
So yeah, okay. I don't have as general class as that, but I used to teach an astronomy grad class that I want to turn into an undergraduate elective, which was astronomy across the electromagnetic spectrum. And really, because it's really interesting. Like, first of all, like what processes you see at different wavelengths, like what kinds of things you see, but also how the technology to detect those works. I mean, it's fundamentally different. I mean, in radio, you have antennas and you're really detecting your light as waves, like that you interfere, and and then you have the ways in which like our CCDs and our all of our phones, like the ways in which we detect visual light photons. But then you get into the X-ray and gamma ray, and you're like actually tagging individual photons. It's like, or like in the gamma ray, you're looking at fundamentally like photons making pairs of particles. Like it's really different physics.
And it gets quantum mechanical.
There's really different physics that goes into So but that's a
Well, that could
astronomy.
be a pretty cool. I'd sign up for that course. I might not pass it.
But
But
no, but I have a lot of fun with that, just because
I audit that.
So I'm going to propose it as an elective course for our astrophysics majors.
As only folks, we can take some of these courses. So open it up to audit.
Okay.
We'll see. Well, this was absolutely terrific. And so you have a group of smart folks who help, they can influence politics and stuff. What would you like the average, relatively informed, scientifically inclined citizen to do? What can we do to support this kind of stuff?
Well, being interested and sort of following, I mean, this is fantastic. Well, one of the things that I really would like to do better is support undergraduate research more. You know, because all the funding agencies that, you know, fund our research, like NASA, NSF, and DOE, they really tend to focus on graduate students. But I think, you know, it is really important that undergraduate students get passion and get their hands dirty, you know, starting to work on stuff. And they are, you know, like most of our research happens in the summer, right? When we don't teach and we have more time, but the undergrads don't have any way to support themselves during the summer. They go home and they sort of lose track. So I think, you know, supporting undergraduate research could really make a big difference.
Actually-
NSFREU.
Yeah.
There's some of that, yeah.
So I would say, yeah, so there are summer programs like the NSFREUs that are just the summer, but I think that there is something that comes out of, I mean, that's like 8 weeks. You can like barely get up to speed on the topic. I mean, we do it. I mean, I've designed 8-week summer projects, but you know, being able to work on something longer term. So actually I wanted to mention, we have a new, it's actually really kind of bringing together people already doing stuff with undergrads, but a new program at UCSC called the Work Study Initiative. So the idea is that, you know, so in particular, I mean, there's the problem of the summer, but even during the school year, I mean, a lot of our students do have to have jobs to help support themselves. And if you're doing, you know, I mean, it's hard enough to get a student to be able to spend time on research just with their normal course load, but if they're also working, those students hardly ever have time. So the Work Study Initiative is, okay, so work study, will pay, I think, I mean, any work study position from government grants, it pays like about half. Right. And so the idea is if you can, you know, come up with the other half, then you can employ them to do actual scientific research instead of like be a lifeguard at the pool or work at the dining hall for those same hours. And so they get the funding for doing like actual research. So I think that's, I mean, so I wrote into my recent NSF grant, we'll see if I get it, funding for that other half. But yeah, programs like that, I think.
So
make a
what
big
percent
difference.
of undergrads at Santa Cruz generally now? How strong are they? I mean, certainly we've had a few exceptional ones, but mostly people not real well prepared.
Well, so I think there's a large variability in the quality of the undergraduate population, and I think we get exceptionally good ones. So at the top end,
Do they
really,
come here specifically for physics and astronomy?
Yes.
Sometimes, yeah. Well, and
Yes.
also like, because we have a really strong transfer student program. I mean, in particular, I mean, we had a former NSF grant bringing in transfer students even before the new like UC mandates on that. So some of those transfer students, they come in a little more mature and, you know, and knowing what they want to do. So I think we're certainly a draw for them.
Probably a big difference between science and liberal arts. And the why students come and things like that. Another idea to tag onto your thing is that most academic learning is class-based, and some of the most rewarding learning is project-based.
Yes.
Yep.
And it could be that this kind of cohort could help with a kid who wanted to do a project. So like Jim, who just got up, could help you with anything to do with computer controls. Hugh would know something. And so I think that if you ever find kids who are undergrads who want to do a project and don't have an oscilloscope or want to learn how to put something together, you could, you know, call us and we could try to hook you up with somebody. And some of us have connections back to industry that might help with some of the other stuff too.
Yeah.
It's just, I want to see more Stefanos and Teslas in the world.
I will say on the undergrads, they do come in with a huge variety of preparation. So the other struggle is the students that are really can be very exceptional, but haven't had the preparation and how to, and actually research if you can do it is a good way to keep them in. But you do have to like, I mean, some of our really best ultimate students just took a little longer to get up to speed, but yeah.
Okay.
So at UC Santa Cruz, do they have, I know at Cal they had something called the 111 lab, which is a junior and senior laboratory where the students are. Do you have something like that where they get that opportunity?
Well, we have an intermediate lab that there's the intro labs, but those are intro labs. There's an intermediate lab, and then they take later also an advanced lab that depends on what their concentration is. So there's a physics advanced lab, and I've been teaching quite frequently our astro advanced lab. But that's usually a more junior, senior level that is more like kind of hands-on astro. Now we've been talking with the astronomy and astrophysics faculty about, changes in the major and maybe some, with an eye towards, it's hard because like our upper division classes can have 100 students in them.
Wow.
So it's really hard to give them those
Wow.
individual.
Yeah, we have a
We have a
very
huge
large.
major. For the number of faculty we have a really large major. And so, but you do want those like practical experiences if you can give them as early on as possible. And so it's hard, but yeah.
And we used to have a